Thank you, Sage. You're exactly right. It is physical science time, and we're talking today about atoms and the periodic table. What is an atom? Where does that word come from? We love to do this, or I love to do this. I'm being really sensitive lately about the differences between the things I love and the things you love. I love to break down these words so I can better understand them because words have meaning. Did you know that? When you say a word to someone, that has meaning. For instance, if you were to say to someone, maybe if you wouldn't eat so many snacks, you wouldn't be so fat. You could say that to someone, and those words have meaning, and that could really sting someone, as an example that I just came up with. But words have meaning, and you can better understand science words, vocab words, if you understand why they're called that. Let me give you an example. If you look into the cell and you see all the little organelles, for one thing, that's a vocab word, the word organelles itself, and it just seems like they have random names to you, almost like a magic spell, then it's hard to memorize the names. But if you realize that the words nucleus and endoplasmic reticulum and Golgi apparatus have particular names because they mean something, either in another language or they're named after someone who discovered them, then that helps you memorize them, or not even just memorize, it helps them become part of your own vocabulary. So atom is a word you probably already know, but the word atom comes from the Greek. This is the Greek letter alpha, is the little like prefix A, and maybe it's Tomos. I think it is like this. And that means to cut. This is the Greek verb for to cut. And what's the A mean? Like, you remember about asexual reproduction? What kind of reproduction is that? Reproduction? Yeah, asexual. What's asexual mean, though? Yeah, without sex, right? Asexual, without sex. So A can mean without, or not, or can't, etc. So the word atom comes from the Greek can't be cut, or without being cut. The idea was, the philosophy was, and this was not provided with evidence, and so it wasn't considered science, but the idea was that a man named Democritus, a Greek, thought, what if I had some, I don't know, cheese or a leaf or something, and I kept cutting it in half, would I eventually get to a piece that was so small that I couldn't cut it anymore? And he called that a tomos, an atom. And that was just an idea. But then when it was discovered later on by Dalton, you know what? I'm trying to decide whether we should write down these people's names or not. Let's do. Thank you for saying that. Dalton's model was that the world is composed of atoms which have the properties of the elements. So elements had already been discovered. You remember from our video that we watched yesterday, who is considered the father of analytical chemistry and who himself discovered many of the elements. The elements were discovered even before him, but do you remember that man's name? From France?
Antoine Lavoisier.
Closer than I was expecting you to get, Antoine Lavoisier. And so elements, the idea, the old medieval or even pre-medieval Aristotelian idea, that is the idea attributed to Aristotle of, or at least formalized by Aristotle, of the world being made of a combination of earth, air, fire, and water, like from Avatar. That idea had kind of been thrown out, and Lavoisier was on the forefront, along with other people, of discovering that these elements are actually the simplest building blocks of nature. That there is a fundamental difference between, for instance, gold and silver, which they had discovered. You know that gold and silver have been known since ancient history. The Egyptians, biblical history, the Mesopotamians. These cultures knew about gold and silver as kind of separate things, but to them, if they thought about it at all, it was thought of as a special kind of earth. Aristotle, the ancient Greeks, thought of these two things as special kinds of earth. That when you combine these, or some earth, with fire, sometimes you get silver or gold, or iron, or many of the elements that we now know as elements had been discovered in what we say antiquity, in the in the ancient olden days, but they were thought of as combinations and not as pure substances. And then that was flipped on its head in the early modern era when people were like, you know what, these things are all different from each other. And Dalton says that because they combine, his evidence was that they combine in fixed ratios. I don't know which exactly elements he used, but for instance, he might say these hydrogens and this oxygen combine in a 2-to-1 ratio to form water, always. And the fact that there is that specific mathematical ratio tells him that these things must be, he thought of them as just solid spheres, that basically like marbles that were made of a pure thing that were so small you couldn't see them and that you couldn't cut them. The elements were each made of little spheres that were so small you couldn't see them and you couldn't cut them, and he reused the term atom for that. Okay? So now there was some evidence. So the atom is now a scientific philosophy, not just Democritus's. Let's attribute this to where it belongs, Democritus. And he lived in 300 BC. If you find that this is wrong, look it up in real life, and if you find that that's wrong, don't at me. 400 BC, your book says, so I was pretty close. But that's a long time ago, right? That's 2,400 years ago that Democritus kind of had this idea. Like he was taking a nap and he woke up, he's like, whoa, what if there was something I can't cut? And that's all it was. It was an idea, but he gave it a name. And then Dalton reused that name to his discovery in the 1800s, your book very helpfully and specifically says. Is this how we currently understand atoms? Do you know? No. The fact that I'm asking that question probably answers that question. No, this is not how we currently understand atoms. But let's get a little bit closer to the truth. You know probably, at least from your vocab and hopefully from 7th grade science, that atoms themselves are actually made of stuff. You remember that? What are the stuff that atoms are made out of? Neutrons, protons, and electrons. For each of these things, one of the state standards tells us that we should know where each of them is located, their mass, and their charge. That's why our objective is model subatomic particles and their interactions. So let's write that down real quick. This could be, you can put this up by your heading, you can put it right here. It's your notes. Model subatomic particles, and that's not the letter and, their interactions. These are the subatomic particles. We already talked about what atom means. I'm realizing now that this cannot be read on camera. I mean, it kind of can. Subatomic particles, but it says subatomic particles. What's sub in subatomic particles mean? Like the subway, like a submarine? Yeah, below. So these are not below in the sense of gravitationally below or physically below, but they're parts of the atom. They're subatomic, right? Subway is a way that is under the ground. Submarine goes under the marine, the sea, right? So subatomic particles are under particles. They make up the atoms. So if these are smaller, right, they make up atoms, how come we don't say that these are the fundamental building blocks of matter? We do say that atoms are the fundamental building blocks of matter. What's the difference? What does your book say is the definition of an atom? We say that it's something that cannot be cut. That's what Democritus says, and that's not even true. Yeah, so an atom is the smallest piece of matter, we now say. An atom, which is made of these things, retains the properties of the element. And what determines what element it is? The number of these various particles. Number of protons is called the atomic number. Let's try to use a little bit better handwriting, Mr. Keim. Silly fool. Atomic number. And this tells us, I'm going to do this in a different color, I think. This tells us what about the atom? What's the difference between manganese and iron? One has more. What do you know what this number means? This is the atomic number, like I said. Yeah, iron has one more proton than manganese. That's what makes it iron. This determines the element. This determines what kind of element it is. In the universe, every atom with 25 protons is different from every atom with 26 protons. They have different properties. There are different things about them. We would say, because we're human beings and we name things, we would say all of those that have 25 protons are called manganese, and they have this kind of properties. And all of those that have 26 protons are called iron, and they have this kind of properties. So far, so good. You're with me, right? So that's what determines what kind of element it is. And where do we find that on the periodic table? In this one, it's this little red number up here. Can you see that they're organized by their atomic number? Where's number 1 at? Where should I look for number 1? Yeah. Oh, it really did break too. That's really sad. Well, hopefully you guys can read sideways. We'll have to fix this later. Yeah, you got it. Actually, it came closer to me, so now I was trying to touch it, and look, now I can. So that's the bright side of this really dark cloud of my periodic table being broken. But look, here, I can get really close to it now. You can see hydrogen. Do you see it? How many protons does it have? 1. What's its atomic number? 1. Now, what about lithium? How many protons does it have? 3. What's its atomic number? 3. What do you name? What would we as human beings name any atom that has 3 protons? Lithium. Are you with me? Every atom in the universe, you do you. Every atom, watch out, Sage. Every atom in the universe that has 3 protons is lithium, and every lithium atom has 3 protons. Okay? The number of, I'm going to try to move this over a little bit so the camera can still pick it up. Number of neutrons tells, I'm going to put, this determines the isotope, and these two things together give us the atomic mass. These two things added together give us the atomic mass. And we'll do more work with that. But effectively, if my atom of, come here, periodic table. If my atom of lithium has 3 protons and 3 neutrons, what is its atomic mass altogether? 6. And the reason for that is that both and only protons and neutrons have mass, so we add them together to get the atomic mass. And we would write that as something like lithium 6. Or we might write it this way, with the little 6 in the top left corner and the atomic symbol Li right there. And then the number of electrons tells us whether or not it is an ion. And this does not have mass, and we'll talk about that in a second, but this tells us the electrical charge. If this lithium ion had an electrical charge of +1, we would write it like this. Lithium, with 6 is its atomic mass, has a charge of +1. So from this information, can you tell me, or maybe you know from previous examples, what is the charge of the neutron? Neutral. It has no charge. What's its mass? Let's put it here. Charge, mass, and location. This is why I made the biggest column the smallest. What's the mass of the neutron? We had here, if it had 3 protons and 3 neutrons, yeah, it has this total mass of 6, and so we say it has 1. What's the glaring question that you would expect me to ask at this point? We can't just say 1. What is the unit? What's the unit for this? It's in, your book says AMU, which stands for, conveniently, atomic mass unit. So that's kind of nice. 1. And there, we usually use these as integers. We don't say 1 point, blah, 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 although it technically is, we say 1. And where do you know is the neutron located? You should know this from 7th grade science. Yeah, in the center, we call the center the nucleus. Nucleus. Things are gotten a little bit, look at all this beautiful white space I have up here. I'm choosing to write it in the tiniest little area. Whatever, your boy can't get it right. What's the charge of the proton? Positive what?
1.
1. What's its mass?
1.
1. Where do you think this guy is located? In the nucleus. Nice. You guys are absolutely killing this. What is about the electrons? Negative 1. The mass?
None.
Yeah, not quite none. It's something like 1 over 1840th the mass of these other ones, but nothing on this periodic table has 1840 electrons, or even whatever half of that would be to make it round up. 920, to make it round up. So we just say they're 0. And where is it located? Yeah, around. Sure. Yeah, sure. Just not in the nucleus, right? Somewhere else besides the nucleus. So we have these subatomic particles, and so was Dalton's model right? Was Dalton's model...
No.
Okay, hey, I actually like that better, Garrett. Yes, it was right to some degree, right? Because what he was saying was that the evidence suggests that when these different elements, which had just been discovered, combine, they do so in fixed ratios. Was that right? Yeah. Was it also wrong? Yes, because they aren't solid spheres of that substance. They aren't solid spheres. They have these parts. The next part to be discovered was the proton, and so Thomson came up with this model. Thomson came up with this model that we sometimes still today even call the plum pudding model. You would be more familiar with it if it were called the chocolate chip cookie model. But his idea was that it is I think he had positive chunks. I'm sorry, electrons were discovered. Forgive me, not protons, electrons were discovered. And so he had this idea of a positive matrix with negative, the word negative starts with an in, negative inclusions. So he called it plum pudding because that was popular in his time. We would maybe call it chocolate chips. It's like the cookie of the chocolate chip cookie is positive and the chips are negative. He understood that since an atom is neutral, it has to balance out. There have to be the same number of positive charges as negative charges. And so the easiest way he could come up with that was that it's this thing that is mostly positively charged but has these negative chunks in it. The thing that had been discovered using the cathode ray experiment, which we will learn about in chemistry, was the electrons that have a negative electrical charge. So someone else just discovered electrons, and to make that work with the current prevailing model, he adjusted the model. Is that a strength or a weakness of science, by the way? That this model, we were like, actually, that's not quite right. That seems weak, right? But that's actually a strength of science, is that when new evidence comes along, we adjust the model. That's good. That's a benefit, right? We don't rely on our proud, like Dalton's cousin could be like, hey, I like Dalton's model better. We don't do that in science. We just say, the new evidence suggests that this is how it is. Is this how it is?
Mm-hmm.
No. Still no. The next discovery was by, or at least the ones that we talk about next, was discovered by Rutherford, where he sees that actually he does an experiment with gold foil where he expects these particles to be reflected back. He fires positively charged particles at a sheet of gold foil, and he expects them to be reflected back. If this is true, if the gold foil is made up of just like a little pile of repeating balls, and it's mostly positively charged, firing positively charged particles at it should reflect them back. But he finds that isn't the case. They mostly go through. Most of them go through. And so he says the atom is actually mostly empty space. Atom is mostly empty space. By what? By mass? No. The things that have the mass are mostly in the nucleus. By volume, the atom is mostly empty space. This might be slightly incorrect, but the example I usually use is that if the football field is the size of an atom, the whole atom, the nucleus would be like a basketball in the middle, and the electrons would be like peas, the size of peas, zooming around elsewhere. So it's mostly empty space. Does that kind of make sense to you? So that was Rutherford's contribution, is the atom is mostly empty space. There's a positively charged nucleus, positive nucleus, with negative electrons kind of zooming around. This is the standard, when you see a cartoon of an atom, it does look like this still. Is this accurate? Well, it's more accurate than these other ones, right? It's not wrong. It is mostly empty space. But The next discovery came when a man named Niels Bohr saw that the electrons actually behave as if they had different energies. That the electrons were not all the same. The electrons have different energies. And so Bohr's model, electrons have varying energy. And he saw this because when you add energy to electrons, they gain some energy, and then when they release that energy, you can see the energy come off of them. And so he developed this idea of the nucleus still in the center, surrounded by concentric rings called orbitals of electrons. Kind of like the planets are in the solar system. Is that accurate, do you think? No, it's not factually accurate. It is true that electrons do have varying energy levels, but they don't actually orbit in neat little circles around the circular nucleus. So we have now this idea, this prevailing idea of the quantum mechanical electron cloud model, where we still have a positively charged nucleus, but the electrons, instead of orbiting in neat little circles, have the possibility of being really anywhere technically in the universe, but they're more likely to be in certain close shapes that we call still orbitals or suborbitals. And the electrons, instead of going around in circles like planets around the sun, what they're actually doing is much cooler. They teleport. They snap in and out of existence. 1 second, or not second, 1 Planck time, they're here, and then the next one, they're completely somewhere else. They don't move like we move. Like if I want to get to my computer, your boy has to, hoof it all the way over here. That's what I have to do. And I do usually walk like that just in my daily life. But an electron doesn't really move so much as it stops being here and starts being somewhere else, which is cooler. That's the electron cloud model. And that is closer to the truth. Right? We get these incremental changes where this one's not wholly wrong, we had said before. Even this is not wholly wrong. I mean, it kind of is. We can separate atoms. But these are not wholly wrong. We increase our knowledge, and we change the model to increase the knowledge. That's true of all kinds of science. The periodic table itself is used to organize these various kinds of atoms. I wish that I still had a periodic table. Maybe, can I have your chair for a second, Sage? This is going to all happen off camera, so if you're watching this YouTube video and I just fall down and break my neck and you just hear gurgling, then that is the end of the video and you can stop watching it. Please be fixed. Oh, it just snaps back in. Okay, I should have done that a while ago. Here is the periodic table. So here we have the periodic table of the elements, a little bit crooked. Let me see if I can make that any better. Come on, get better. Okay, that's a little less crooked. It's still somewhat crooked. But here is the periodic table of the elements. This one happens to be copyright 2017, Flynn Scientific. Other brands are available. But the periodic table is a beautifully organized thing. You have to believe me. The more we learn about it, the more you will see for yourself how beautifully organized it is. But one thing that's so beautiful about it is that atoms in the same family, that is the same vertical column, with me so far, right? What's the vertical column called? Family, or sometimes called a group. Atoms in the same family have similar properties. Does that remind you of anything from your life where people maybe have similar features but are not identical? What would we call that? A family. I was just commenting the other day about how much Garrett and his sister Alexa look similarly. They have very similar noses and what is this? Faces. And skin tone. Even as I look right now across the room at Garrett and his good buddy Lucas, they have different skin tones and different faces and different noses. But both Garrett and his sister have similar properties, and Lucas and his sister have similar properties. Do you know what I mean by properties? Skin color, hair color, eye color, etc. They're not the same. Do you find that Garrett and Alexa are not the same human being? That's correct. They aren't the same, but they are similar. And so lithium and sodium, while not identical, do have similar properties. Both of these things, we'll do this in the lab sometime, if you drop them in water, will explode. And so that's a similar property. Does all of this stuff explode when dropped in water? Absolutely not. But these two do because that's a property they have. Over here, these two are both gases, and they're both extremely toxic, reactive gases that if they get in your eyes, your eyes will melt. So not everything here, if it gets in your eyes, although don't put any of this in your eyes, will make them melt, but these two will because they have similar properties, because they're in the same, they are the same family. And we'll learn in the next chapter about what these families are called and some of their explicit properties. But for now, it's good enough that you know that these have similar properties, and these going across are called periods because they periodically change throughout the various properties. If we look at this period, we'll see that it has, you can even tell from up here, it has a light metal, heavy, 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 ductile heavy, etc. You can see there's, if we look at these, if we listed them out, you would see a similar pattern emerge of purple, purple, red, blue, 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 yellow, 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 etc. And it changes from period to period, but they are each periodic. That's why we call it the periodic table of the elements, because they cycle through different properties as we go from one line to the next. Those are called periods of the periodic table. Who is considered the father of the periodic table? You should remember from your reading. No, it is not George Washington. It's a Russian named Dmitry Mendeleev. I'm going to write it up here. Dmitry, I'm not actually going to write on this. Dmitry Mendeleev, if you want to spell his name, it's in your book. Dmitry Mendeleev came up with the idea. And the story is that he was like snowed in Russia, because that's what one does in Russia, and he had arranged each element that was then discovered on something like playing cards, and he was trying to think of different ways to organize them, because they were just, Lavoisier just organized them in a list, write down. And so Mendeleev was organizing these things, and he was late for some meeting or something, and he came across the way of organizing them like this, and he's like, oh, this is really good, and then he published a paper on it and wrote a textbook about it. The periodic table of elements, ladies and gentlemen.